Yes.
Oh, good.
Yes, completely okay. We'll start.
Okay, so in this, myself, Ari Kasari, I'm a PhD student, and I was working with my supervisor, Dr. Peter Popov, who presented earlier at the plenary, and Professor Raj Kumar Roy, the safety of connected autonomous vehicles, specifically the safety monitors and perception, but this time not just when a hazard's happening, but also when it's an attack, to see how a cyber attack would now have implications on safety. We'll start with an introduction just to kind of introduce CAVs and all the safety, then a bit of state of the art, our research objectives, followed by the main part, which is actually our models, the introducing the software, the hazard model and its different components, followed by the attack model, what kind of parameters we've set for the experiments, the results we've got, and a bit of a discussion, and then look at our conclusions and any work we plan to do on future. So, recent increase in automated systems has kind of led to more of a hands-off approach by human beings, and one of these examples is the connected autonomous vehicle. The machine's going to have to do some of our job. It means more connectivity, more information is going to be needed. However, this does increase the attack surface, especially when you're linking to things like Wi-Fi and networks and having sensors, because now you can have attacks on your perception, attacks through the communications. As much of an issue if it was just a computer system, because we would just deal with the computer side, but now we've got something like a vehicle which is cyber physical, so the computer system could actually lead to something like a car crash. We're mostly going to focus on like the perception system, the hazards, and the safety model. So we're going to see the vehicle trying to deal with hazards and perceive them by a malicious user who could probably be doing it remotely. As we know that perception is a key part of autonomous vehicles, perception, we know that if this part fails or doesn't function properly, for example, it's delayed for some reason, or one of the key components, such as sensor breaks, we're going to have issues, especially if a hazard suddenly pops up. To look at the hazard perception model when it's under attack, because there's been safety, there's been security, but this overlap is where it gets really serious, because cyber physical systems are now a fairly new area. Let's go into some of the ideas behind CAVs. So, side part, working our way towards the inside of the vehicle, it starts with the communications. So we've got vehicles communicating with each other, to communicate, their intentions and other information they may have gained, because if they all have as much information as possible, decisions can be coordinated and safer. Vehicle to infrastructure, because if we have infrastructure from different areas communicate with one another and give information from vehicles, we can organize traffic across longer distances. Information then goes into the actual vehicles, such as sensors, as well as the communications, will then go into the embedded subsystems of the vehicle called the ECUs, connected via a line network, which is typically the controller area network, or CAN bus. Quite fast, doesn't really have much security, and you don't need to really upgrade or install anything. You connect them, they have a CAN transceiver, they will communicate immediately. Some of these ECUs are connected to sensors. Many sensors are usually vulnerable with things like spoofing, where you can kind of give information that misleads it, like convincing it that it's either further away, the obstacle, or closer, which essentially the sensor is completely blinded by your attacker. And one of the more recent papers we've read, I think a 2022 one that came out very recently, was one where you could essentially blind it in such a way where you don't blind it fully, but you essentially delete a pedestrian from the view of the vehicle, so it keeps going as if it's not even in front of it. Our research objectives, basically our aim is to assess the safety capability of CAVs, specifically in the perception, under attack, how is our safety affected? For the sake of this experiment, that false hazards aren't happening. So if a hazard's happening, it's definitely real. So it's there, we've either seen it or we haven't seen it. And our results should give us an idea of when we individually compromise different parts of the hazard perception system, what the effects are. Without any of the parameters that will be activated in an attack, as well as all of them, to kind of get an idea of only when no attacks are happening and how it works when you've successfully compromised the entire system. So now we'll go on to the SAN model. So this is stochastic activity networks, which allow us to essentially have a sort of state machine in time occurring at different rates. For example, you could have hazards occurring at a certain rate, the accidents happening at a certain rate. The attacker could be attacking every few hours. This in the Mobius software, which is from Illinois University. This software also allows for simulations such as Monte Carlo or the use of a numeric solver to control not only the time period across which we simulate, but the degree of accuracy, so like how many decimal places we want our values to. We have a lot of parameters and we plan to expand them in the future to more different cases. We found that the numeric solver was just much faster as it generated the states in advance and there was less of them. So all of our tests have been done using a numeric solver. Model of the vehicle observing different safety implications for basically 7 experiments. The baseline, the worst case, and the main 5 parameters modeled separately that I will describe further ahead. So firstly, this is the hazard model just on its own. I think if people watching the plenary earlier with Peter, they saw a similar model, but this one has been modified because we're taking into account attacks. State would, for example, have different scales built into these timed activities. So it could be like 3 times more likely to cause a certain event to happen. First thing we would be ignore that branch that goes student C, OK to FH, because we are not accounting for false hazards. So that's not going to do anything in the case of what we've done for this research. At a time of 100 hours, going up to 9,100 hours. A lot of states here, as you can see, like the OK state, that's before we start going to hazard perception. Falsely perceived hazard, we're not considering. You can perceive a hazard correctly or you can overlook it, which could then lead it to delay. And then it could either be perceived correctly at a later time, which could shorten the reaction time to deal with it, or in many of the cases, you just go to an accident because you haven't managed to deal with it in time or detect it. Essentially, these are the different states and timed activities, because things like the OK to hazard is having us, for example, have a hazard occur at a fixed rate, and then the probability of either detecting it correctly or overlooking it, at which point you could either just continue to overlook it or detect it later, which could again lead to an accident. Time is one of the more interesting ones because this is where you've got the delay from the overlook. So you could either not see it and go straight to an accident, or you see it later and now maybe because you're closer than usual to the hazard when you've got to deal with it, it could still lead to an accident, or you could just manage to clear it on time. Or the third option is that a hazard actually goes away, or for example, if a vehicle in the middle of the road and you think you're seeing that as a hazard, it clears it. This is the part that gets slightly different from just a hazard model. We've now linked it to a very generic attack model where we assume an attacker is always ready, attacking periodically at a fixed rate and succeeding with some fixed rate. When it succeeds, it would be compromised, which is linked to the compromised state in our hazard model. Now that takes effect and starts to put into play parameters that we want to test, make overlooking a hazard be more likely. Periodically resets the attack, because otherwise our model would just be constantly compromised and we wouldn't really get to see much difference. the attacker's ready, then they go into actually performing the attack, which they'll either succeed or fail. They could compromise the system, and the attackers just reset every once in a while. Now we get into the actual experiment. So these are our parameters that we're looking at when the system is compromised, and we're putting them on one at a time. So firstly, the hazard scale is basically if we have a value for hazard scale, and that's what happens when you don't detect the hazard. So the vehicle's going along, there's a hazard, it just doesn't detect it. Base scale, so you could still detect it, but much later. So if you detect it earlier on, the vehicle can deal with it faster. Scale, this is more how you actually deal with the hazard. So it's detected the hazard, to deal with it, make the correct maneuvers, brake, etc. H to CH, this was essentially when the hazard is overlooked and you've still got to correct it. So when you've just completely overlooked it, this means an attack that makes you just overlook a hazard. The late CH to accident scale is similar to accident scale, but now it's late. So dealing with a hazard that you've detected late. We had a series of fixed parameters that were for our timed activities. So these meant controlling like rates of accidents given that we had a correctly perceived hazard. Essentially meant that we were at false hazard. Just the rate of the hazard overall, just for the attack rates. And finally, we assumed that the RSS, so the safety system, was not perfect, because that would be an ideal assumption, which is less realistic. And as you can see, experiments 1 through 7, we started with none of these parameters active. So accident scale meant when the system is compromised at accident scale meant, like, for example, your rate at which you're failing to deal with something could become 10 times as much. Created these individually for 5 experiments and then activated all of them once, so we could compare them to both the best case baseline and our worst case. So we then plotted all of these together, and as you can see, just about everything except for accident scale is the same as baseline, meaning their effects are essentially negligible. So we tabulated them as well, which is in the paper as well, because the graph wasn't showing them well enough. And we see that essentially one of the key things when you're dealing with these parameters on their own, so an attack that's compromised just the delay scale on its own is negligible, whereas if you compromise the vehicle's ability to deal with the hazard, physically take action, you have a serious issue, as it seems to essentially reach 100% likelihood of an accident at around 3,100 hours. Case is going to always give you the worst result, ideally, in this case. So we determine the following from it. A baseline, this is basically just how good the vehicle safety is when it's not being attacked, how it's dealing with hazards. Likelihood of dealing with an accident, yeah, this on its own is a serious problem. So how it takes action. Delaying hazards or failing to detect them or otherwise is negligible on its own, but looking at the worst case cause serious issues. It's like the worst safety implications possible. So we can see that whereas accident scale on its own has the most effect, we see that if worst cases combined, we should consider looking into combinations of attacks on different parts. So the attacker gets in and compromises different parts of the hazard perception and safety monitors of the vehicle. So our conclusion is that individually attacking parts of the vehicle has very little effect, and that therefore we need to consider looking at the combined attacks. So for example, what if you attacked delay scale and accident scale together? We kind of see the path of an attacker, which would give us an idea of where defenses should go. But additionally, false hazards, because we didn't consider them, we need to see if, like, an attack that makes the vehicle think there's a hazard when there isn't one could lead to actions that actually make the vehicle a hazard to other vehicles on the road as well. Based off those conclusions, we are going to do combined attacks to see like which combinations have the worst effect on vehicle safety, and then even perhaps introduce defense models, either to many components at once and some of them, just to see how it affects safety implications in the presence of attacks, as well as testing false hazards. But we'll do these one at a time and then combine them all. If there are any questions, I will attempt to answer them to the best of my ability at this point.
Thank you for your presentation. And dear participants, please, your questions.
Thank you for your presentation, Area. Two points. First of all, I think there is a standard called CANFD that actually supports the security on the ECU level of messages, and that's actually the part of the intrinsic safety of the vehicles. How did you analyze that part? Do you refer to the intrinsic safety built into the different parts and pieces of the vehicle?
I think the model is quite very generic at this point. It hasn't modeled a specific CAN component or anything. It's more of just a model that's looking at how it's dealing with hazards in general. But if we were to model like the CAN, that would have to be like its own model looking at all the rates at which like information is communicated and stuff.
Okay, understand. The second question is, in my mind, I think that the general reliability and the hazards protection of vehicles is somewhat connected to the vehicle readiness in the broad terms to carry out its main business function, meaning driving. How do you see the standardization impact in that regard? Because apparently if there is some sort of spoofing, then the vehicle can just stop and just not move. That's it.
Yeah, that is definitely a major concern, especially like a jamming attack. That's what I was saying. If it convinces it that there's something in front of it, then depending on the RSS policy, it's going to stop in the road. And if it suddenly has to do this, then it could get rear-ended by a car.
Okay, and what the solution could be is vehicle-to-vehicle communication, or how do you see that?
I think there would have to be a mixture of the good RSS policy, vehicle-to-vehicle, and just to be able to kind of tell when a sudden detection prior to not having seen anything happens, just to be able to tell.
Thank you very much.
Thank you. My very short question about, what about, you talk about combination attack, yes?
Yes.
As I know, there is a problem of blackout for automotive infrastructure. Company Cisco informed about such cases. Can your approach to describe such kind of attacks and domino effect for vehicle-to-vehicle systems? Thank you.
I think it depends. If you're talking about infrastructure blacking out, that depends if that's a fault or if like the infrastructure is being subject to a denial of service attack by like a rogue entity pretending to be vehicles communicating with their vehicle. That's pretty close range. So provided it's not impersonation, it should be good.
Okay, sorry, I did not hear last your sentence. Please repeat last your.
Oh, vehicle to vehicle. I know that's pretty short range, so they communicate when they're close to one another. So provided it's that an attack isn't happening, which to be fair, that could be worth investigating as well, is that vehicle works well normally, its performance up compared to an attack, for example, like civil attacks, where they're pretending to be multiple vehicles communicating to mislead another vehicle in terms of how it changes direction.
Okay, thank you. Any other questions? No, thank you very much, Ariel Kalsari, for your presentation. Thank you. And thank you very much, all participants, all reporters of our session. Thank you very much, moderators, Dr. Nikos Doukas. And today our program very successfully finished, and see and hear you tomorrow on the our morning plenary session. It will be two very interesting presentation from industry and from Italy Institute of System and Technology, Information Technologies. Any questions? No. Thank you very much one more. See you and hear you tomorrow. Thank you.
Thank you.